Chapter P1, we're going to be going over algebraic expressions, mathematical models, and the set of real numbers. So before we get into exponential notation, just the definition of a variable here up top. A variable is just a letter used to represent various numbers, and typically we use x or y. It doesn't have to be x or y. We can use just about anything. So getting into exponential notation is going to be what we have here, b to the n. So this b is the base, which is why I'm writing it as a b. The n up here is the exponent, so it's a superscript. It's the exponent or the power that the base is being raised to. So what that means is b to the n is going to be b, the base being multiplied n times the exponent number of times. And like I just read it, b to the nth power, or b to the n. And an important note here, which we'll go over in a little bit, b to the 0 power equals 1, and b to the first power just equals b. Okay, so some examples of this. Let's say we had start with 7 to the 0. So 7 to the 0, what I just mentioned, b to the 0, anything to the 0 other than 0 is equal to 1. Let's do 9 to the first power, that's equal to 9. Then we'll do 8 to the second power. So based on the definition up here, that means 8 times 8. 8 times 8 is 64. So 8 to the second power, we multiplied it together twice. And when we have something to the second power, we can say that that is squared, 8 squared. And let's do 5 to the third power. So that would be 5 being multiplied 5 times. So 5 times 5 times 5 is 125. When we raise something to the third power, we can say cubed. So that would be 5 cubed. And maybe one more here, 2 to the fourth. 2 being multiplied 4 times, and we get 16. So squared and cubed are just our kind of shorthand ones because they tend to pop up the most for us. So the next thing for an algebraic expression is going to be just an expression, so no equal sign, which can consist of variables, numbers, addition, subtraction, multiplication, division, and maybe some exponents or roots. So for example, something like 3x plus 6, this is an expression, there's no equal sign. Or something like x squared minus 3, that's also an expression. So we're going to be evaluating expressions. In order to evaluate expressions, we need the correct order of operations. So we need to evaluate them in this order. So we're going to do whatever is inside the parentheses first, if there is any. Then we're going to do the exponents. And then we're either going to do multiplication or division, whichever one comes first from left to right. And then same thing after that, we're going to do addition or subtraction, whichever one comes first from left to right. So if we look at the first letter of each word here, that is Pemdas. So you can use that to help you remember the order of operations. And just remember that the M and D, multiplication, division, are essentially the same, whichever one comes first, left to right. Same thing with addition and subtraction. So let's do a couple examples here. So use the order of operations to simplify each one. So 8 squared minus 16 divided by 2 squared times 4 minus 3. So we would have to do parentheses first, but there aren't any. So exponents are first for this one. 8 squared is 8 times 8, which is 64. And then we have 2 squared. So I'm going to ignore everything else. 2 squared is 4. Okay, so next would be multiplication or division, whichever comes first from left to right. So we have a division and multiplication. but we're going to do 16 divided by 4 first. 16 divided by 4 is 4. So now we're going to do the multiplication. 4 times 4 is 16. And now we just have subtraction. So it's going to be 64 minus 16. So I'm going to put this up here. So 64 minus 16 is 48. Minus that 3. 48 minus 3 is 45. So our answer would be 45. Next, for B, we have 8 minus 3, and then we see brackets and parentheses. So brackets are just the same thing as parentheses. We just tend to use them if we have more than one set of parentheses. So we have 8 minus 3, and then times negative 2 times 2 minus 5 minus 4 times 8 minus 6. So parentheses first. So we go to the bracket. We want to evaluate what's inside the bracket first. There's parentheses inside there. So that means we have to evaluate this set first and this set first. So it's going to be 8 minus 3 times negative 2. 2 minus 5 is going to be negative 3 minus 4 times 8 minus 6 is 2. So now we're going to evaluate what's inside the bracket. So we have multiplication in there and subtraction. So we're going to do the multiplication first. So negative 2 times negative 3 is positive 6, minus 4 times 2 is 8. Okay, and then we're going to do that bracket, which is just parentheses. 6 minus 8 is going to be negative 2. Multiplication next. Negative 3 times negative 2 is going to be plus 6. So this expression is going to equal 14. And for another one here, we have 10 divided by 2 plus 3 times 4 divided by 12 minus 3 times 2 squared. So I'm going to deal with the numerator and denominator separately. So the numerator, we have division and multiplication and addition. So division first because it pops up first, left to right. 10 divided by 2 is 5. So 5 plus 3 times 4. In this denominator, we have an exponent, but we have parentheses, so we need to evaluate that first. Inside the parentheses, we have multiplication. So we have to evaluate 3 times 2, which is 6. Okay, so now for the numerator again. 3 times 4 is 12. Denominator, we have to do the parentheses still, finish them up. 12 minus 6 is 6. So it's a good habit to leave parentheses around something if it's raised to an exponent, even when you're done. It won't matter with positive numbers, but it will with negative numbers, so it's good practice to leave it there. Oops. So 5 plus 12, 17. 6 squared is 6 times 6, so 36. So I'm just going to leave that just as 17 over 36. Okay, so let's make these a little bit harder. So we're going to be evaluating algebraic expressions now. So that means we're going to be finding the value of an expression for a given value of the variable. So all we have to do is plug in whatever number, and then use the proper order of operations again. So let's do this first one. So let's evaluate 7 plus 5 times x minus 4 cubed when x is 6, x equals 6. So I'm going to plug that in. I'm going to plug in a 6 into x. So 6 minus 4 cubed. And now it's the same exact thing that we were just doing. So order of operations, parentheses first, 6 minus 4 is 2. So next is going to be the exponent. 2 cubed is 2 times 2 times 2, which is 8. 7 plus 5 times 8, we need to do the multiplication. 5 times 8 is 40. And 7 plus 40 is 47. And next, we have 6 times 23 minus x squared minus 2. And we're going to evaluate that when x is 13. So let's plug in a 13 into x. So 23 minus 13 squared minus 2. Parentheses first, 23 minus 13 is 10. Exponent next, 10 squared is 10 times 10, so 100. Multiplication, 6 times 10, 600. And 600 minus 2 is 598. Okay. All right, making these even a little bit more challenging, there's something that we do have to watch out for. When we have so this note up here, a negative number, if it's raised to an odd power, you're going to get a negative number as the result. If the negative is raised to an even power, you're going to get a positive number. So let's see what I mean by that. So let's evaluate x squared for x equals negative 2. So when we're plugging this in, we need parentheses around it. Negative 2 squared. So negative 2 squared, we know that is negative 2 times negative 2, right? Just based off of exponents. Negative times a negative is positive. So 2 times 2 is 4, so it equals positive 4. So that's a negative to an even power. It became positive answer. Let's see what happens for the next one. X cubed, let's evaluate x cubed when x is negative 3. So that's going to be negative 3 cubed. We know that means negative 3 multiplied together 3 times. So it was raised to the power of 3. So what that means is that we're going to have a leftover negative when we multiply, so our answer is going to be negative. So the first two negatives will make it positive, but the odd one out will make it negative, and 3 times 3 times 3 is 27. So negative 3 cubed is negative 27. So a negative to an odd power is negative answer. Next one, x to the 5th for x equals negative 1. So it's going to be negative 1 to the 5th. So we could write this out as negative 1 times itself 5 times, or we can recognize that that the exponent is odd and the base is negative, so we know it's going to be negative answer. 1 raised up to the 5th power is just 1. So negative 1 raised up to an odd power is negative 1. Negative 1 raised up to an even power would be positive 1. And for x to the 4th, evaluate x to the 4th for x equals negative 2. So that's going to be negative 2 to the 4th. So right away I see that it's raised to an even power, so we know it's going to be positive. 2 to the 4th is 2 times 2 times 2 times 2, which is 16. So if you have to write this out in expanded form being multiplied, that's fine. I'm just skipping it for now. And for the next one, we have x plus 4 squared minus 3 for x equals negative 5. So we're going to plug that in. Negative 5 plus 4 squared minus 3. Simplify parentheses first. That's negative 1 squared minus 3. Negative 1 squared, that's a negative to an even exponent. 1 times 1 is just 1. So that's 1 minus 3, which is negative 2. And for the last one here, 2 times negative x minus 3 cubed for x equals negative 1. So this is going to be plugging in a 1 into x, so negative 1 minus 3 cubed inside here. Negative 1 minus 3 is negative 4 cubed. Negative 4, it's a negative to an odd, meaning it's going to be a negative answer. Negative 4 times negative 4 times negative 4 is going to be negative 64. Negative 64 times 2 is going to be negative 128. Circle these. crowded. Okay, and then just an important note that I'm going to write down here. Negative x squared. This equals negative and then x squared, meaning it's going to be negative. This is not the same thing as negative x, where negative x is in parentheses and then squared, because this is equal to positive x squared. So parentheses 100% matter. Okay, for the next thing, so that was evaluating expressions. The next thing is going to be working with equations. So an equation is going to be formed simply when there's just an equal sign between two algebraic expressions. So for example, if we have something like 2x minus 3 equals 4x cubed. So this whole entire thing is going to be an equation. Both sides of the equal sign are their own individual expressions. Okay, and then the next thing here is going to be a formula, definition of a formula. So a formula is an equation. A formula is an equation that uses variables to represent a relationship between two or more quantities. So for an example of this is if we had something like f equals 9/5 times c plus 32. So what this is, usually formulas are solved for one of the variables. So it's solved for f here. This is actually the conversion between degrees Fahrenheit and Celsius. So you could plug in degrees Celsius here to solve for Fahrenheit. We could solve this for Celsius if we wanted to. If we solve that for C, we would get 5/9 times f minus 32, which we'll actually be getting into solving stuff like that later on. Hey, and the process of actually coming up with formulas to describe real-world events would be an example of mathematical modeling, which is used all the time in applied mathematics in different disciplines. So let's do a couple examples here. So let's use this formula up here that I just wrote down, to convert the given Celsius temperatures to its equivalent temperature on the Fahrenheit scale. So we have, essentially we're asking for the first one, what is 20 degrees Celsius in Fahrenheit? So what we're going to do here is we are going to plug it in. So it's going to be F equals 9/5 C plus 32. So let's plug in C equals 20. So 9/5 times 20 plus 32. So all we're doing here is working with multiplying fractions first. 9/5 times 20 is 9/5 times 20 over 1. What we can do is we can simplify. We can either multiply 9 times 20 and then divide it by 5. Let's make the numbers easier. Let's divide 20 divided by 5 first. 20 divided by 5 is going to give us 4. Now it's easier to work with. We can do all of this whole thing in our head. 9 times 4 is 36, so 36 plus 32 is 68. So this means that 20 degrees Celsius equals 68 degrees Fahrenheit. And let's do negative 40 degrees Celsius. Let's see what that is in Fahrenheit. So 9/5 Celsius plus 32. We're going to plug in negative 40 into Celsius. So once again here, let's simplify so it's a little bit easier for us. So negative 40 divided by 5 is negative 8. Plus 32. And 9 times 8 is going to give us negative 72 plus that 32. So negative 72 plus 32, this is negative 40. So you're probably saying, well, hey, that's the same thing that we just started with, negative 40 degrees Celsius. That is because negative 40 degrees Celsius is actually equal to negative 40 degrees Fahrenheit, which is pretty cool if you didn't know that. Pretty cool how they are equal at that point. Okay, let's do one more here. So we have the formula T equals 4x squared plus 330x plus 3,310 models the average cost of tuition, which is the T, for public U.S. colleges for the school year ending X years after 2000. So we want to use the formula to find the average cost of tuition for the school year ending in 2012, or 2010 rather. Okay, so we need to figure out, we're looking for T. So we're looking to find T when X is what? When X equals what? So we're trying to plug in for X. So the school year ending in 2010, X we were told represents X years after 2000. 2010 is 10 years after 2000. So X here is going to be 10. So we are using this formula. And we are going to plug in 10. So it's going to be, let me erase this T. So it's going to be 4 times 10 squared plus 330 times 10 plus 3,310. And now just order of operations once again here. So it's going to be 10 squared is 100. I'm just going to leave the other stuff the same for now, which we could have evaluated it. So I'm going to do both of those multiplications. 4 times 100 is 400. Plus 330 times 10 is going to be 3,300. And lastly, we multiply all these, or we add them all together, and we get 7,010. So this means the tuition for the school year ending in 2010, based on this mathematical model, is going to be $7,010. Okay, so mathematical models are typically used, or typically created, given previous data. Okay, so kind of switching gears here just for a little bit. We're going to get into sets of numbers. So we're going to be using this throughout the course. A set is just a collection of objects whose contents can be clearly determined. And the objects in a set are called the elements. So things inside of a set are just called elements of the set. And we denote a set using braces, which I call them squiggly brackets because they're squiggly brackets, but they're technically called braces. So two ways to represent a set here. We're going to have the roster method and the set builder notation. We'll pretty much be using both of them. So roster method completely just lists the elements out in the set and uses commas to separate them. So roster method, and just lists them out. So here we have the set of natural numbers. If you remember from the previous section, set of natural numbers, we have just 1, 2, 3, 4, and so on. These are called the counting numbers. Make a little note. Set of natural numbers. And we also call these the counting numbers. And I don't know if we mentioned this before, but I'm going to mention it now. The ... here obviously means continues in this fashion, or and so on. It's called an ellipsis. So it just means continues in this fashion. So that's the roster method. It's pretty simple. It just lists everything out. The next one is not as simple. It's the set builder notation. The elements are not listed in set builder notation, but they are described. So for this, it looks something like what I have written right here. So what we're going to do is we read this as this first part here. We start by reading it as the set of all x values. This vertical line is read as such that. And then everything after that is the description. It tells you what you're referring to, or what is in this set. So this is the set of all x values such that x is a counting number less than 6. So if we were to write this in the roster method, a counting number less than 6 is a natural number less than 6, which means it's going to be 1, 2, 3, 4, and 5. So we can see how it's described here but not listed out. But we just listed it out using the roster method. So a lot of the time set builder notation will come in handy when there's too many things that we can actually physically list out. Okay, so next thing that we're going to be doing is the intersection of sets. So for the intersection of two sets, we write that like this with that little cap, and we read that as A intersects B. It's the set of elements common to both A and B. So if we were doing a Venn diagram, and this was set A over here, this circle was set A, this circle was set B, the intersection of the sets, you can just think of the word intersection normally. It's where they intersect. It's where they overlap. So it's the sets where it's the portion where they have in common in the middle. So let's do these examples. So let's find the intersection of the sets. So these are all in roster method. So we have the first set, 7, 8, 9, 10, 11. We want to see when does that intersect 6, 8, 10, 12. So all we have to do is say, well, what numbers do they have in common? And the numbers that they have in common are going to be, they both have an 8, and they both have a 10. So it's pretty simple. And for the next one, we have, when does the set 3, 4, 5, 6, 7 intersect 3, 7, 8, 9? So once again, what do they have in common? They have a 3, and they both have a 7. So 3 into 7. And just make sure that when you're writing your answer for this, the answer is also a set, which is why it has the squiggly brackets. Okay, so if a set has no elements, not every set has elements in it, it's called the empty set, or sometimes called the null set if you want to. It's represented with the symbol, looks like a little circle with a line diagonally through it. Technically, there's another way to denote it. It's just by drawing the squiggly brackets, but not putting anything in it. Obviously, that one doesn't look as good to me personally, so I just like using the other symbol. So for example, if we try to determine the intersection of these sets, 2, 4, 6, 3, 5, and 7, we're saying what do they have in common? They have nothing in common. So we would say that this is the answer is the empty set. The intersection of these two sets is the empty set because they have no elements in common. Okay, so that's intersection. The next thing is the union of sets. So the union of sets A and B, two sets A and B, we use the little cup notation, looks like a U for union, is going to be the set of elements that are in A or in B. So it's what is in both of the sets essentially. So essentially it's just every single thing in the sets. So once again, let's look at a Venn diagram here. And circle A is on the left, circle B is on the right. So the union would be everything in both of the sets here. So both of them are just shaded in. So union, let's do this example. Let's find the union for the following: 7, 8, 9, 10, and 11 for the first set. We want to find the union of that with 6, 8, 10, and 12. So what we're going to do is we are just going to list out everything that's there. One thing to keep in mind though is we don't have to repeat something if it's there in both of them. So we have a 6 in the one on the right, 7 on the left. They both have an 8, 9 on the left. They both have a 10, 11 on the left, and 12 on the right. So union pretty much means join, right? So essentially we're just joining the sets together to make one big set. Let's do 2 more. So we have the set 3, 4, 5, 6, 7, union 3, 7, 8, 9. So I'm just going to write everything down, join the sets together for the union. They both have a 3. There's a 4 on the left, 5 on the left, 6 on the left. They both have a 7, and then 8, 9 on the right. And for the last one here, we have 1, 2, 5, 8, 13, union 3, 4, 8, 9. So just copying everything down again, we have 1, 2, 3, 4, 5, 8, 9, 13. So intersection of the sets are what they have in common. The union is joining the sets together. It's everything in both sets. So that brings us into some definition of other sets here. So we've already done the set of natural numbers. So the set of natural numbers, we can denote that with a capital N. Oops. With a capital N, except with a like double backbone. And that's going to be the set of numbers 1, 2, 3, 4, 5, 6, 7, 8, and so on. Next one, set of whole numbers, which we can denote with a W with a little double backbone again. So the set of whole numbers are the natural numbers, but including 0. So it's going to be 0, 1, 2, 3, 4, 5, and so on. So it's the natural numbers plus the set of zeros, plus 0. So what we could say here is that the natural numbers are a subset to the whole numbers because the natural numbers are contained inside of the whole numbers. Next one for integers, it's not denoted with an I, it is denoted with a Z. Integers are positive or negative whole numbers. So what I'm going to do for this one, I'm going to put an ellipsis on the left and say -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on. Okay, so it's positive and negative whole numbers for the integers. So the whole numbers are a subset of the integers because they're contained in there also. Next, for the rational numbers, so rational numbers gets a Q because the R is already taken, which we'll get to in a second. So rational numbers are going to be, this one can't be listed out very nicely in roster method, so I'm going to write this one in set builder notation. So it's going to be the set of all fractions such that the numerator A and B are integers. So the word ratio is in the word rational, right? So rational numbers are ratios of integers. So for an example of this, we could have something like -5. We can write this as -5/1, right? -5 and 1 are both integers, so whole numbers and integers, so just integers. Integers are rational numbers because we can just place them over 1. Another one we can have is 2/3. 2 and 3 are both integers, so this works. If we think about this as a decimal, this is 0.6 repeating. So repeating decimals are actually rational numbers because we can rewrite them as a ratio of integers, which may not seem like it, but we can. And if we have something just like 2/5, that would be 0.4. 2 and 5 are obviously integers. So terminating decimals like 0.4, those are also rational numbers. Okay, next one, irrational numbers. Going to denote this with a kind of a cursive looking I, just because I don't know how to do a backbone non-cursive I. So for these ones, I'm just going to kind of write out the definition in words here. It's going to be any number whose decimal representation is neither terminating nor repeating. So irrational numbers are going to have, if you wrote them as a decimal, they would go on forever. So they would never stop. They would keep on going, but they would also never repeat. So a couple commonly used examples for this. Radical 2, so the square root of 2, which if you plug this in the calculator would be something like, put a squiggly equal sign here, would be about 1.4142135, and it's going to keep on going. And it's going to keep on going forever, and it's never going to repeat itself. Okay, another one is pi. So hopefully you remember pi. Pi is approximately 3.1415 and so on. So that's also going to go on forever, and it's never going to repeat itself. So radical 3 is irrational, radical 5 is irrational, radical 7, radical 11. So a lot of radicals are irrational numbers, because we cannot write them as a ratio of two integers. So lastly here, the set of real numbers. The set of real numbers, so this one gets the capital R. So the set of real numbers is going to be, I'm going to write this in set builder notation. It's going to be the set of all x's such that x is rational or irrational. So rational and irrational numbers together, the union of them, make up the set of real numbers. So almost everything that we work with is a real number. Any number you can think of almost is a real number. The ones that are not, that we'll be getting to, are imaginary numbers. They're not real numbers. We'll worry about that at a later date. And the infinities are also not real numbers. Okay, so let's do an example to make sure we know that we're comfortable with this. So let's say we have these set of numbers here. We have -7, -3/4, 0, 0.6 repeating, radical 5, pi, 7.3, and radical 81. So we're going to go through and see which one of those numbers are in all of these sets. And they can obviously be in multiple sets because a lot of these sets are subsets of the other ones. Okay, so let's do natural numbers. So let's skim this for natural numbers. We know natural numbers are 1, 2, 3, 4, and so on. So skimming this for one of those types of numbers, we get to radical 81. Radical 81, the square root of 81 is actually equal to 9, which is a natural number. So that means radical 81 is a natural number. We'll be getting into working with square roots more also. Okay, so for whole numbers, we know that whole numbers are natural numbers and also 0. 0 is in this set, so this is going to be 0 and the square root of 81. For integers, integers are going to be whole numbers, but also including negative whole numbers. There's a -7 up here. So that's going to be -7. 0 is an integer, so is radical 81. And for rational numbers are going to be numbers that can be written as a fraction, as a ratio, with the numerator and denominator being integers. So this is going to be -7, -3/4 works, 0 works, 0.6 repeating works because we can write that as 2/3. Radical 5 doesn't, pi doesn't. So 7.3 up here can be written as 73 over 10, which is so it's a terminating decimal, so we know it's a rational number. Can be written as a ratio of integers. So that works. And so does radical 81. Lastly, for irrational numbers, that's just going to be radical 5 and pi. Okay, and then for the real numbers, we're going to have everything. So rational numbers and irrational. So I'm just going to list them all out. -7, -3 over 4, 0, 0.6 repeating, radical 5, pi, 7.3, and radical 81. All right, for the next thing, so a couple more things left for this section. The real number line. So the real number line is essentially a graph, and we use it to represent just the set of real numbers. So it just looks like this. I'm sure we're familiar with it. We have 0 here in the middle. So everything to the right are positive numbers, and everything to the left are negative numbers. And the numbers increase from left to right. So we can actually use inequalities to help us compare the values. So the inequalities we have are less than or equal to, greater than, and greater than or equal to. So you can see right here, I have them listed out. So the inequality sign opens up to the larger number. And if it's or equal to, we have one of the equal to slashes below it. So for the first one, A is less than B, and then second one, A less than or equal to B, and then A greater than B, and A greater than or equal to B. So some examples of this, we could have -4 less than 2, which we obviously know is true. Positive is greater than negative number. Could have -3 greater than or equal to -7. So the negatives, you just have to make sure you're a little bit careful. -3 is greater than -7. It's further to the right on the number line. The or equal to, that's completely fine. So it's greater than or it is equal to. It's greater than, so it suffices. -5 less than or equal to 0, that also is true. And 9 greater than or equal to 9. So that last one looks a little weird, but it says or equal to, so technically that's true because they are equal. And for the next thing here, we have the absolute value, which we'll be thinking in terms of the number line also. So the absolute value of a number, which we'll call x, it's denoted by the vertical lines to the left and right of it. So that's the absolute value of x. What it is, it's the distance from 0 to x on the number line, which is always going to either be 0 or positive. So technically, the technical definition I wrote right here, this is called a piecewise function. It's chopped up in terms of the domain, which we'll get to that also. So it says the absolute value of x is going to equal -x if x is negative. That means if we're negating a negative, it becomes positive, or it equals x if x is greater than or equal to 0. So it just equals the positive number if it's already positive. So it looks confusing, but that's a technical definition for it. And if this isn't an expression where we're simplifying, we would kind of treat them like parentheses at first. We would evaluate the inside of it, inside of the absolute value. So let's do some examples, start off simple. So let's rewrite each expression without the absolute value bars. So we have the absolute value of 3. So this is saying how far away is 3 from 0 on the number line, which is just 3. For -2, this is absolute value of -2. How far is -2 away from 0 on the number line? That is 2 units. So all you have to do is just drop the absolute value bars and make what's inside of it positive, and that's it. But you should think of it as a distance from 0. For negative absolute value of 5, the absolute value of 5 is 5, but there's a negative out front. Order of operations says we have to keep it negative afterwards. Another way of thinking about this is -1 times the absolute value of 5. So this would be negative 1 times 5, which would be negative 5. And then for negative absolute value of negative 7, the absolute value of negative 7 is 7, but we still have the negative out front, so that's negative 7. 17 minus 23 is inside the absolute value for part E here, so we have to simplify that first. 17 minus 23 is negative 6. Absolute value of negative 6, positive 6. So let's make it a little bit harder here. So we have the absolute value of 2 minus pi. So we almost never, unless we're doing like a word problem type thing, we don't really want to use an abbreviation or an approximation for pi or irrational numbers. We know that 2 minus pi is negative. 2 minus pi is negative because that's about 2 minus 3.14-ish, so that's going to be negative. Since that's negative, all we have to do to come up with an equivalent expression for that and drop the absolute value bars is reverse the order. Reverse the order and drop absolute value. So what that means is this equals pi minus 2. So the distance from zeros are going to be the same here. So for the next one, the absolute value of radical 3 minus 1. So radical 3 minus 1 is actually positive. It's 1 point something. So that means we do not need to reverse the order. So do not. Oops. So we don't need to reverse the order, but we can just drop the absolute value bars and we'll be good. So this just equals radical 3 minus 1. So there's nothing wrong with that. I know it looks probably looks messy, but that's completely fine. There's no other way of writing it where it's 100% accurate because we would have to round if we use the decimal. Okay, one more for this particular one. So we have negative 2 times 4x plus 10 plus 2, and we're going to evaluate it for x equals negative 5. So let's plug in a negative 5 into x. So it's going to be 4 times negative 5 plus 10 plus 2. So Pemdas, order of operations, we need to simplify what's inside the absolute value first. There is multiplication. 4 times negative 5 is negative 20. And we still need to simplify what's inside of there. Negative 20 plus 10 is going to be negative 10. Now we have the absolute value of negative 10, which is positive 10. So drop the absolute value bars. Negative 2 times 10, negative 20 plus 2 is going to give us negative 18. Okay, and for next thing here, let's simplify this following expression, and this will be the last thing for this whole entire page. So we have this long, nasty expression with division. What I'm going to do here is simplify the numerator, denominator separately. So we have absolute value bars in the numerator, so I'm going to simplify what's inside of those first. So 12 divided by 3 times 5 times the absolute value of 2 squared plus 3 squared. Exponents first inside here, so that's going to be 2 squared is 4, 3 squared is 9. Denominator, we have an exponent. 6 squared is 36, so it's going to be 7 plus 3 minus 36. Numerator, we still need to simplify what's inside those absolute values, so that's going to be 4 plus 9 is 13. Denominator, 7 plus 3 minus 36. 7 plus 3 is 10. 10 minus 36. And for the numerator now, we just have multiplication and division. So it's going to be 12. I'll do 12 divided by 3, because it's the first one from left to right, which is 4, times 5. The absolute value of 13 is just 13.
10 minus 36 for that denominator is negative 26. I'm going to bring this up here a little bit. And now we have 4 times 5 times 13. So we'll see in the next section with the order of multiplying with the associative property of multiplication, we can multiply these in any order. So if we just did 4 times 5, we would get 20. If we multiplied that by 13 next, we would get 260. So 260 over negative 26 is going to give us negative 10. So our answer for this whole thing actually simplifies to just negative 10. Okay, so that is it for P1.